Hello and welcome to the Maths 2 component of the online degree course on data science. In this video we are going to talk about equivalence and similarity of matrices. So, we want to impose a certain equivalence or what is called an equivalence relation based on two different relations. We are going to study this on the set of matrices. So, the first one is called equivalence. This is on the set of m by n matrices and then the second one is for square matrices. So, the reason we want to do this is because there are certain what I will call invariants. This may not make sense right now, but that is fine, called eigenvalues that you are going to see later on, and these will come up not in this course, but in the data science part that you will see in the subsequent semesters. Where you will use these for certain calculations. Okay, so without bothering about everything that I said before, whether or not it made sense, let us get into the nitty gritties of what is equivalence and similarity for matrices. Okay, so let us consider two. We will first talk about equivalence of matrices. Let us consider two matrices of order m by n. Both have the same order, remember. So, we say A is equivalent to B if B is equal to Q times A times P. So, we can find matrices Q and P which are invertible. So, P has to be because it is invertible, because I impose the condition of being invertible. First of all, they have to be square matrices, and since we are saying Q A P, that means A is, remember, m by n, that means P has to be n by n and Q has to be m by m. So, they have to be invertible matrices and B has to be equal to Q times A times P. So, you have, if we can find Q and P or P and Q such that B is equal to Q times A times P, meaning when you compute Q times A times P you get B, then we say A and B are equivalent or A is equivalent to B. So, the other way of viewing this is by doing our good old row and column operations. So, if you can perform a series of row operations on A and then a series of column operations on A, so that you can then obtain B, then we will say that A is equivalent to B. Yeah. So, you take all the column operations on the right. So, you get P and you take all the row operations on the left, and that is how you get Q by multiplying successively, that is. So, we have seen this idea before, and I am just trying to motivate how to get Q and P if you want to actually get them, but we will see a different way of getting them. Okay. The other characterization is that the rank is the same. So, the reason this works is because remember that if you allow both row and column operations, then you can take any matrix and reduce it to the form where you have block matrices, where you have the identity matrix 0 0 0. I will say that carefully in a second. Okay. So, equivalence of matrices is an equivalence relation. So, what is an equivalence relation? So, I am not defining it, but what it means is A is equivalent to itself. Remember that we say A is equivalent to B if there exist P and Q, so that B is equal to P times Q times A times P. So, A is equivalent to itself is saying that there exists some Q and P, so that A is equal to Q times A times P. Now, I think it is clear what Q and P should be, we will write it down in a second. So, A is equivalent to B implies B is equivalent to A, again because of invertibility of P and Q, this is clear, and A is equivalent to B and B to C implies A is equivalent to C. Okay, so let us quickly write down how to do this. A is equivalent to itself because you can write A as identity m cross m times A times identity n cross n. Of course, identity matrices are invertible. A is equivalent to B implies B is equivalent to A. Well, we know that A is equivalent to B, that means B is equal to P times Q times A times P, and that implies by multiplying by the inverses that A is equal to Q inverse times B times P inverse. So, A is equivalent to B that is what we started with, that means B is QAP, that will imply that B is equivalent to A. So, because we can write A as Q inverse times B times P inverse. So, that means you can multiply on the left by some invertible matrix and on the right by some invertible matrix to get A from B. So, B is equivalent to A. Okay, and then A is equivalent to B and B to C implies A is equivalent to C. This is because B is equal to QAP, C is equal to, let us say, Q prime B P prime. Then you can replace B by the first part. So, C is equal to Q prime times Q times A times P times P prime. And now Q and Q prime are invertible, that means this product is invertible. Similarly, P and P prime are invertible, so this product is invertible. So, I have a invertible matrix on the left and on the right, which I can multiply to A in order to get C. So, that is why A is equivalent to C. And now we can just say A and B are equivalent, because this is an equivalence relation. So, once you know that A is equivalent to B, B is also equivalent to A. So, we can just say A and B are equivalent. Okay. So, from now on I may sometimes say A and B are equivalent matrices, that means A is equivalent to B or B is equivalent to A, both are the same. Okay. Now, let me come back to this rank of A is rank of B. What I meant here was that you can get Q and P, so that QAP is of this form, and you can also get Q prime and P prime, so that Q prime B P prime is of this form, and then that is why A is equivalent to this matrix here, if we call it C, and B is equivalent to this matrix C, but this is an equivalence relation, that means A is equivalent to B. So, that is one way of checking that if rank of A is rank of B, then indeed they are equivalent. Conversely, if they are equivalent, then I'll leave it to you to check that indeed the ranks are the same. That is a little bit of manipulation of column and row spaces. Okay, so we know what it means to say that two matrices are equivalent. So, let us look at the linear transformation f from R3 to R2 given by f of x y z is x plus y and y plus z. So, let us consider two ordered bases for R3, the standard ordered basis and another ordered basis, which is 1 1 0, 0 1 1 and 0 0 1, and let us consider two ordered bases for R2, which is the standard ordered basis and the basis 1 0 and 1 1. So, let us express the standard ordered basis for R3 in terms of the standard ordered basis for R2 after applying f. So, if you apply f to 1 0 0, you get 1 plus 0 comma 0 plus 0. So, that gives you 1 0. If you apply f to 0 1 0, you get 0 plus 1 and 1 plus 0, which is 1 1, and then you write it in terms of the standard basis, which is 1 times 1 0 plus 1 times 0 1, and then if you apply f to 0 0 1, you get 0 plus 0 and 0 plus 1, which is 0 1, and that is just 1 times the second vector in the ordered standard ordered basis. So, if you want to write down the corresponding matrix for this linear transformation, that is corresponding to the ordered basis, standard ordered basis for R3 and standard ordered basis for R2, you get 1 0, 1 1 and 0 1. So, where is this 1 0 coming from? It is coming from here. Where is this 1 1, the second column, coming from? It is coming from these coefficients, and the third one is coming from these coefficients. This is something we did in our previous videos. Okay. Let us do the same thing for the other two bases. So, the other ordered basis for R3 and the other ordered basis for R2. So, if you look at f of 1 1 0, that is 1 plus 1 comma 1 plus 0, so that is 2 1, which you can express as 1 times 1 0 plus 1 times 1 1 in the ordered basis, the second ordered basis gamma 2. Similarly, if you take f of 0 1 1, this is 0 plus 1 comma 1 plus 1, which is 1 comma 2, and for this if you write it in terms of the ordered basis, it gives you minus 1 times 1 comma 0 plus 2 times 1 comma 1. and for the last one you have f of 0 0 1, which is 0 plus 0 comma 0 plus 1, which is 0 1, which is minus 1 times 1 0 plus 1 times 1 1. So, if you look at the corresponding matrix, first column is going to come from the first equation coefficients, the second column is going to come from the coefficients of the second equation, and the third column is going to come from the coefficients of the third equation. So, it will look like 1 1, minus 1 2 and minus 1 1. Okay. So, what have we done so far? We have taken a linear transformation and we have written down two matrices corresponding to two different ordered sets of ordered bases. Okay. So, choose P to be this matrix 1 0 0 and 1 1 0 0 1 1 and Q to be 1 minus 1 0 1. So, this is something I produced out of the air, and here is what happens. So, then Q times A times P, this is something you have to compute. I have done the computation here. This is 1 minus 1 0 1 times 1 1 0 0 1 1. So, this was A times 1 0 0 1 1 0 0 1 1. So, if you multiply this out, let us see what you get after doing the first multiplication. You get the first row in out of these two is so 1 minus 1 times, so this is 1, then this is 0, then this is minus 1, and then you have 0 1 1, and you want to multiply this to this matrix. So, if you do that, let us see what we get. So, if you do 1 0 minus 1, indeed you get 1, then 1 0 minus 1 times 0 1 1, that is minus 1, and similarly a minus 1. So, this first row is indeed achieved, and then for the second row you take 0 1 1 and multiply it over there. So, that gives you 1 2 and 1. So, indeed the second row is achieved. So, if you do this multiplication yourself, you will be able to see that Q times A times P is indeed equal to B. So, these matrices are equivalent to each other. Okay. So, this is not some magic. So, consider a linear transformation T V to W and two ordered bases beta 1 and beta 2 for V and two ordered bases gamma 1 and gamma 2 for W. Okay. So, like in the previous example, where we had V was R3, W was R2, and beta 1 and gamma 1 were the corresponding standard ordered bases, beta 2 and gamma 2 were some other fixed ordered bases. So, we took A to be the matrix corresponding to beta 1 and gamma 1. So, similarly here you take A to be the matrix corresponding to T with respect to the bases beta 1 and gamma 1, and you take B to be the matrix corresponding to T with respect to the bases beta 2 and gamma 2. This is exactly what we did in the previous example. Okay. Then A is equivalent to B. So, the previous example is an example of this phenomenon that we have mentioned here. So, the question is, how do I get Q and how do I get P? So, for P, express the basis beta 2 in terms of beta 1. Okay. And for Q, express the basis, I should say ordered basis, everywhere we have ordered basis, the ordered basis gamma 1 in terms of gamma 2. So, this is how I got those two matrices. Let us quickly look at that example again. So, let us look at this example again. So, if you look at the matrix P, the matrix P is exactly expressing this basis here 1 1 0. So, this is 1 times E 1 plus 1 times E 2 plus 0 times E 3. So, this 1 1 0 goes into your first column, and similarly each of these. So, you have 0 1 1 which goes into your second column, and 0 0 1 which goes into your third column, and so that's how I get P. And for Q, what I did was I wrote 1 0 and 0 1 in terms of 1 1 and sorry, in terms of 1 0 and 1 1. So, this is 1 times 1 0 plus 0 times 1 1. That is why I get 1 0 in my first column, and 0 1 is minus 1 times 1 0 plus 1 times 1 1. That is how I get minus 1 1. Okay. So, this is a strategy for getting P and Q, and this works for any general linear transformation and these fixed ordered bases beta 1 beta 2 and gamma 1 gamma 2. So, yeah, so to complete this, express this, get P and Q from there, and then you will find that B is equal to Q A P. Okay. So, this is something you have to check. I will leave it at that, since this is not really a proof based course. Okay. So, we have exhausted equivalence. Let us look at similarity of matrices. So, now we are going to restrict ourselves to square matrices. So, we will say that two square matrices of size n by n are similar, or rather we will say that A is similar to B. So, we have two n by n matrices A and B, and we will say A is similar to B. If there is an invertible matrix P, it has to be of size n by n, such that B is equal to P inverse A P. So, now the role of Q is being played by P inverse. So, this is a very big change. So, if you can express B as P inverse A P, then we will say that A is similar to B. So, again similarity is an equivalence relation, by which we mean A is similar to itself. A is similar to B implies B is similar to A, and A is similar to B and B to C implies A is similar to C. Let us quickly see why this is the case. So, for the first one, again you can take P to be identity, then A is equal to identity inverse A identity. Well, identity inverse is identity. So, this is just identity times A times identity, which is certainly A. For the second one, let us see how to do the second one. These are on the same lines that we have done the previous part. So, A is similar to B means B is equal to P inverse A P, but that means because P is invertible, I can multiply by P inverse on the right and P on the left. So, I get P B P inverse is equal to A. So, just rewriting that, P is equal to P times, so I want to write this as P inverse inverse. So, why did I write it like that? Because I want to express this in terms of the inverse of whatever is occurring on the right term, P inverse times B times P inverse. Now, you take your P inverse, call it something else, call it P prime if you want. Then we have an invertible matrix P prime such that A is equal to P prime inverse times B times P prime, which is exactly saying that B is similar to A. So, the second one is satisfied, and the third one again was on the same lines as we did our previous part. So, let us see. So, we have B is P inverse A P and C is let us say Q inverse A Q. These are both n by n invertible matrices P and Q. So, then C is equal to my bad, this is not B, but this is not A, but this is B. So, C is equal to Q inverse, and now you put in the values, put in the first equation, which is B is P inverse A P into the second. Then you get Q inverse P inverse times A times P Q, but remember Q inverse P inverse is exactly P Q inverse. Okay. And now, if I call P times Q as something else, let us say P prime, then this is saying that C is equal to P prime inverse times A times P prime, which says that A is similar to C. So, this proves the three things. So, this says that similarity is what is called an equivalence relation. So, now I can say, especially because of the second one, instead of saying that A is similar to B, I can just say A and B are similar, because it does not matter which is similar to which, the other one always follows, right. So, A is similar to B can be replaced by saying A and B are similar matrices. Okay. So, why do we really care about similar matrices? So, the reason we care about similar matrices is because of some of these properties. The first is that A and B are equivalent. This is clear because equivalent means that there is P and Q. So, that B is Q times A times P, where P and Q are invertible. But if they are similar, then you can take Q to be P inverse and P to be P. So, this is clear. A and B have the same rank as a result. The determinant is the same. Now, this is a big difference. Remember, now we are in square matrices. We couldn't have made any such kind of statement before. The determinant of B is determinant of P inverse times AP, but determinants multiply, if you remember. Then that means this is determinant of P inverse times determinant of A times determinant of P. But now, although matrices do not commute, real numbers do, and determinants give you real numbers. So, I can write this as 1 by determinant of P, because determinant of P inverse is 1 by determinant of P, times determinant of A times determinant of P, and then because these are real numbers, I can shift 1 by determinant of P to the right, and then determinant of P divided by determinant of P gives me 1. So, I get just determinant of A. So, they have the same determinants. This is a very useful property, and this is one of the properties that you will be using later on, not in this course, but in a different course for certain reasons. So, the reason in fact is that there are other invariants. So, one such is called the eigenvalues, which you are going to study later. Okay. So, I have written some names here, and this you are not expected to make sense of this, but it will be good if you remember this just as a statement without understanding when you do your next course. So, several other invariants of A and B are the same, such as the characteristic polynomial, the minimal polynomial, and the eigenvalues with multiplicity. We are not going to define this right now, but this is just as a feeder into the next course, where you will be using some of these things, especially this thing called the eigenvalues. Yeah, so just remember this name. Doesn't matter if you don't understand what it is now. Okay, so this is why we are studying this idea of similarity. Let's do some examples, or maybe one example. So suppose you have a linear transformation f of x y z is minus x plus y plus z, x minus y plus z, and x plus y minus z. Now we are going to use the same basis. Yeah, earlier we had two different bases, right? So we had beta 1 and gamma 1, and then we had beta 2 and gamma 2. But here remember that this linear transformation is from R3 to R3 itself, right? So we are going to use the same ordered basis. So let's start with beta being gamma being the standard ordered basis. Okay, so let's do what we did before. Let's express f of 1 0 0, f of 0 1 0, and f of 0 0 1 in terms of the standard basis. If you do that, you get f of 1 0 0 is minus 1 1 1, f of 0 1 0 is 1 minus 1 1, and f of 0 0 1 is 1 1 minus 1. So that means these things exactly end up being the coefficients when you write it in terms of the standard ordered basis, and as a result the matrix of f corresponding to these the standard ordered basis is coming from these give you your first column, these coefficients give you your second column, and these coefficients give you your third column. Okay, let's choose some other basis. Beta prime and gamma prime is the same. So this is the same. So this is beta prime and it is also gamma prime. So let's express this f of each of these vectors in terms of as linear combinations of these vectors themselves. So if I do f of 1 1 1, I get back 1 1 1. Let's remember what the linear transformation was. It was minus x plus y plus z, x minus y plus z, and x plus y minus z. So in that case we get f of 1 1 1 is minus 1 plus 1 plus 1, 1 minus 1 plus 1, 1 plus 1 minus 1, which is 1 1 1. So which is the first vector itself. So this is 1 times 1 1 1 plus zeros for the zeros in the coefficients for the other vectors. F of minus 1 1 0 is minus of minus 1, which is 1, plus 1, plus 0, which is 2, then minus 1 minus 1 plus 0, which is minus 2, and then 1 minus 1, rather minus 1 plus 1 plus 0, which is 0. So, you get 2 minus 2 0, and f of minus 1 0 comma 1 is again you will, if you do it, you will get 2 0 minus 2. And now, if you write these in terms of the vectors that you have, the second 2 minus 2 0 is just 2 times the second vector, or rather minus 2 times the second vector, and the f of the third vector is minus 2 times the third vector. So, what we have got is there is a basis here which is beta prime. So, that when I apply f on that basis for these particular vectors in the basis, they just scale, right. So, f of 1 1 1 is 1 1 1, f of minus 1 1 0 is minus 2 times minus 1 1 0, and f of minus 1 0 1 is minus 2 times minus 1 0 1. Okay. So, for this particular basis, the linear transformation behaves very nicely, it just scales. Yeah, one of the vectors remains the same, so it scales by 1. The second and third vector gets scaled by minus 2. Okay. So, the corresponding matrix is a diagonal matrix 1 0 0 0 minus 2 0 and 0 0 minus 2. And now, we know that diagonal matrices are particularly easy to understand, right. So, what we see here is that we have the same linear transformation in terms of one basis, the standard ordered basis. We got a matrix which was not hard, but maybe not so easy. But in terms of this basis, this new basis beta prime ordered basis, we saw that it is a diagonal matrix. Okay. Now, let P be 1 minus 1 minus 1, 1 1 0, 1 0 1, compute P inverse. This is something you can do, I have done it here. It is 1 third, 1 third, 1 third, minus 1 third, 2 third, minus 1 third, minus 1 third, minus 1 third, 2 third. And now, if you multiply, so you look at P inverse AP, then you get, if you multiply this carefully, I have done it here. So, I will suggest you check that this calculation is correct. You get the matrix B. So, this last matrix is exactly your diagonal matrix B. So, you get that A and B are similar matrices. So, what have we seen? We have seen exactly what happened in equivalence. The same kind of thing is happening for similarity, but this time instead of having different bases, your beta and gamma are the same ordered basis, okay, because your vector space V and is the same vector space, it is V and V. So, you have a linear transformation from V to V. So, here we have R3 to R3. So, you take the basis beta and beta, in our case we took the standard ordered basis, and you got the matrix A, which is this matrix here. And in terms of a different ordered basis, which we call beta prime, where implicitly gamma prime was equal to beta prime, we got this matrix. So, remember that now the basis that you are choosing on both sides are the same. So, the beta and gamma have to match, okay. And then if you write down these matrices, they end up being similar matrices. So, this is a general phenomenon. Let us look at another quick example. So, f of x y is 2x comma y. So, if you look at the ordered basis 1 0 and 1 1, you can look at, so f of 1 0 is just 2 0, f of 1 1 is 2 1, and you can write this in terms of the basis that you have 1 0 and 1 1. So, this basis is, if you want, beta and gamma both, and as a result the corresponding matrix is the coefficients coming from here, coefficients which go into the first column, coefficients from there which go into the second column. So, it is 2 1 0 1. Instead, you can look at the standard ordered basis. So, this is this time your beta prime and gamma prime, and it is clear, it is 2x comma y. So, f of 1 0 is 2 0, f of 0 1 is 0 1. So, this is scaling your first vector by 2, and it is retaining your second vector as it is. So, this gives us a diagonal matrix 2 0 0 1. So, let P be 1 1 0 1, P inverse is 1 minus 1 0 1, you can compute this. And now, if you compute P inverse AP, this is a very simple calculation which I have done here. you get your diagonal matrix, which is exactly the matrix B. So, this is exactly B. So, the matrices 2 1 0 1 and 2 0 0 1 are similar. So, we have seen two examples where we took linear transformations from two vector spaces to themselves, expressed each time these linear transformations as basis with the same basis on both sides. So, and then we changed the basis, again with the new basis on both sides we computed the matrix, and we saw that these matrices are similar. So, this is a general phenomenon, and the proof for this is exactly the same. So, consider a linear transformation T V to V and two ordered bases beta and gamma for V. Let A be the corresponding matrix with respect to beta and B be the corresponding matrix with respect to gamma. Then A is similar to B. So, that means I have to produce P. How do I produce P? To produce P, you write, so express, so we want that B is P inverse AP. So, express, so for P you express you express gamma in terms of beta, okay, and P inverse is well, you can get it from P by inverting, or you can get it from B by expressing beta in terms of gamma. What does this mean? This means you take each in an ordered way. You take so this first one means you take the first vector of gamma, write it as a linear combination of the vectors from beta. Take the second vector of gamma, write it as a linear combination of beta, and so on. So, you get that. So, if you have n many, you write all those n many things, and then you get a matrix. For the first equation that you have, put the coefficients into the first column. For the second equation, put them into the second column, and so on. For the nth equation, put them into the nth column. That is your matrix P. Same thing, but the opposite way, that is your matrix P inverse, or you can get it just by inverting P, and you will find that you end up with B is P inverse AP. So, again it is not a proof based course, I won't prove this fact, but this is how you get P. Fine. Why do we care about similarity? I mean, this is maybe the most important question. So, the reason is that, as we saw in the previous two examples, sometimes, so we hope, so the underlined part is we hope, because under some basis we hope that the corresponding matrix is a diagonal matrix, which gives an easy geometric understanding of the linear transformation, right. So, if you have a diagonal matrix, as I said, it is saying that some particular vector scales, some other particular vector scales, and some third vector, let us say in R3 scales, and it is giving you how much it scales by, and these three form a basis. So, that is the intuitive picture you have in mind. So, let us quickly recall what we have done in this video. We have seen the notion of similarity and equivalence of matrices. Equivalence was, both of these are equivalence relations. Equivalence is for rectangular matrices, I mean, which means matrices which need not be square. So, we say they are equivalent if B is QAP, then A and B are equivalent. For similarity, we say that B is P inverse AP. I mean, if B is P inverse AP, then we say A and B are similar. And these notions are useful because they sort of help you to understand how to go between different bases on a vector space. If you have a particular linear transformation and you choose different bases, how do you go between the corresponding matrices? That is really what equivalence and similarity is telling you. And similarity is particularly important because it may so happen that your linear transformation may not, the algebra that when you write it down, it may look like a very difficult entity, but under some particular basis it may suddenly start looking very nice. This is really the main point behind why we study similarity. Okay, so thank you for your attention.